Hi students, welcome to lecture 40 of our course. Today I am going to talk about endurance of propeller powered aircraft, and as you know, endurance is the time the aircraft takes to fly in the air, and essentially there are a lot of aircraft which are designed such that they need to spend a lot of time in the air. So these are typically when you are into something like a reconnaissance or a surveillance mission, for example aircraft flown by the Navy or the Coast Guard. I'm Dr. Ranjan Ganguly. Now, let's again begin with the equations we have discussed before also, but do keep in mind that we are discussing about the propeller aircraft today. And so what happens is that the power required equals drag into velocity, and the power available is equal to power required if we are considering steady level flight, and this is equal to d into v infinity, where d is the drag and v infinity is the velocity of the airplane. Now, the fact that we are considering steady level flight means that thrust is equal to drag and lift is equal to weight. So these are equations we are going to use in this particular lecture. Now, what happens is that all the power which is produced by the engine is not necessarily available to the aircraft. So what happens is that some of this power is lost. So there is one more equation, that is PA equals eta into P, where capital P represents the brake power output of the engine, and the available power is related to this through the efficiency of the propeller system. So we can write P equals PA divided by eta, which becomes equal to dv infinity by eta. So this is the equation which lets us calculate power as far as the propeller aircraft is concerned. Now we are going to use this equation for power in the endurance equation, which I derived a couple of lectures before. So the general endurance equation, you can go back and look at it, is integral w1 to w0 dw by cp, and we can now substitute for p here. So p was dv infinity divided by eta, which is put in here, and then I rewrite this slightly in a different form. So what I do is that I multiply and divide this equation by W, and then I use the fact that W equal to L. So that is how I am able to bring in lift into this equation here. So remember that L is equal to W, so I can do this L and W here. And the reason I do this is that I want to express this in some form involving lift and drag. Now this equation has one more variable we want to change, and that is v infinity, and to do that I again go to the equation lift equals to weight. So this is equal to half rho infinity v infinity square SCL. So do remember that S is the area of the wing and CL is the lift coefficient. So from this equation I can get the equation for v infinity as root of 2w by rho infinity SCL. So this is the equation which we then put into the equation for endurance again, and so I put in this value of v infinity here, and so this is the equation of endurance which comes out. So you can clearly see the first two terms are here, that is eta by c, then L by d becomes CL by CD. The v infinity has been replaced here, so what we have done is flipped this. So the rho infinity SCL has gone into the numerator and the 2 into the denominator, and there was a w there also. So the w is a square root or a half, so there is a w here. So the w and the w half becomes w 3 by 2. So essentially we can add the indices of w to the power 1 and w to the power half, and so we get w3 by 2 here. So this is the equation now which we are able to express purely in terms of the weight, and then there are these remaining parameters. Now before we discuss further, I am going to again review the basic definitions of weight and how they are changing in the aircraft from the point you take off to the point you land. So essentially at the point you take off, the weight is W0, that is the gross weight of the airplane, and at the end point it is W1, which is the weight of the airplane without fuel. And so what happens is that between these 2 points, the relationship is that W1 equals W0 minus WF. So WF is the weight of the fuel here. And of course, this equation is immediately going to tell you that W0 is greater than W1. So you start out with a full tank of fuel, and at the end of your mission, the fuel tank is typically empty. So now what happens when you do performance for an aircraft for endurance is that you fly and you land at a different destination, or you may land at the same destination, but essentially what transpires between these 2 points A and B is that time is dissipated. So essentially you have started from some time t1 and you end at some time t2. So we are interested in this time here. We are not interested in distance as was the case with range. So now we can actually calculate this integral if we had all the variations of this with weight, but to get a closed form solution we are going to presume that all these values are constant. So CL is constant, CD is constant, eta is constant, C is constant, and rho infinity is constant. So again, recall that C is the specific fuel consumption here, eta is the efficiency of the propeller. So if we take all these things out of the integral, then we are left with dW by W3 by 2, and we can integrate that. So remember, from calculus we take it to the numerator, that becomes W minus 3 by 2, and then we add a 1 to it, so that becomes W minus half. So that's how we get this minus half term, and then we have the bounds of the definite integral between W1 and W0. So that gives us this equation here, which I have put in this yellow. So this is a very nice use of calculus here, and so we get a closed form solution for endurance. So now we are going to look at this equation very carefully and see what we can extract from it in terms of physics. So let's take a look at this equation, which is the endurance for a propeller aircraft. So again, we see that we typically want to maximize the endurance E, and so what we can do is maximize eta, which is efficiency of the propeller system, have a low C, which is have an efficient fuel system, and also we can fly at the highest value of CL3 by 2 by CD. So this is different from the expression for range. Now we have CL3 by 2 by CD, whereas in range we had CL by CD. Also we see that density has come up in this equation for endurance. So essentially the density should be as high as possible, and that is the case when you are at sea level or at a very low altitude, because to remember from standard atmosphere that as you go high up, the altitude will come down. And so these are the basic parameters here, and we are going to look at the weight in the next slide. So let's look at the weight term now. Now you can clearly see this weight term. I can write it like this, and I can simplify it. So essentially this negative half, I brought it down to the denominator, so it became half here. And then I use the fact that W0 is W1 plus WF. I do that here, so I get this equation. Now we can clearly see that we want to maximize this particular term here, so that will essentially maximize endurance. And to maximize this term, what I should do is I should have a high fuel weight, because if I have a high fuel weight here, then this term is going to get maximized. It's going to become more. So that's something we try to do here. Again, we try to fly this aircraft with a high level of fuel weight. So let's now compare the formulas we have obtained for the propeller aircraft. We can now write the range and the endurance equations. The equations on top are given in the integral form, and the equations at the bottom here, these are given in the closed form solution. So here the yellow things are referring to the range equation, and the green boxes are referring to the endurance equation. So one thing we clearly see here is that endurance is a function of density, but range is not. And therefore what would happen is that endurance would change depending on the height at which we are flying for a propeller airplane. So of course all these judgments we are making are based on the assumptions involved here. So we made a lot of approximations to get into these equations, so you need to keep that in mind. But it's a very interesting situation. We can see here that endurance would be maximum if you fly at a very low point, and that's often the case that when you are designing a propeller aircraft, you typically look for missions where you fly low. Maybe you fly short haul between two cities. Maybe you are designing a UAV, which is mostly going to loiter at low heights so that it can loiter around the ground and so on. And so, wherever such kind of situations are involved, where you have an endurance driven mission, then you can consider a propeller if you are going to fly at low altitudes, because that's going to maximize the endurance. So to summarize, this is the equation for the propeller endurance, and you can clearly see that now we have certain factors, like we have CL3 by 2 by CD. So the design goal is going to be quite different compared to range. So if you are designing an aircraft for endurance, then the aerodynamic design is going to be mandated by CL3 by 2 by CD, and also it's going to be driven by density and the weights, of course, the weights at the end of the mission and the weight at the start of the mission. So remember, W0 is the gross weight, which is the weight when you start the mission, and W1 is the weight at the end after you have expended a lot of the fuel. So this was my lecture for today. So we have now looked at range and endurance for a propeller aircraft, and we have obtained some physical insight from some of these formulas. And like I discussed before, these formulas are not completely accurate because they consider the aircraft to be in cruise level steady flight, and therefore we are making those approximations that thrust is equal to drag and lift is equal to weight. So they are not considering takeoff and landing situations. So that's something to keep in mind, that you do have to go through climbing flight and landing flight and so on. But like I mentioned before, the answers you get from these formulas will be 10 to 20% off from what you get from the actual numerical integration. So in many cases, this is much simpler to get. And of course, you can derive a lot of physical insight from these formulas and closed form solutions. That's very often something which is done in math modeling of most engineering systems, is we try to derive formulas for simple situations, because then what happens is that we can extract a lot of physics out of that model, and that helps us build physical understanding about the system we are designing. So that was my lecture for today, and I will see you in the next lecture when we are going to start discussing about the jet airplanes. See you then.